Yes, so my name is Dhavide, by the way. So I'm an applied mathematician and computer scientist. I used to work for Quantside. I worked for Anaconda for a little bit. I was a university professor for a while. All right, so without further ado, let me get started. Okay, so the first thing we want to do is set up our EarthData credentials. Once we've done that, also in this folder, there's some instructions here about using this hub, which some of you are able to use and I'm not. But once you've done that, what you'll need to do is make a local configuration file .netrc, which you can do by just running python.make netrc. You can either do it by executing this cell in this notebook, and I get a warning because it already exists, which is fine. I don't need to do it. But if you haven't done it, the other thing is you can do it in a terminal, or you can even just edit it and you put in the relevant data that you just created for your user, your EarthData cloud. And if you've done that correctly, you should be able to run a little test. And what the test does is it goes out on the network, it reaches out, it does a search query, and we'll figure out what all of these things are, and it checks to see whether or not I've set up the credentials correctly. Now I'm doing it locally on my own machine instead of on the cloud machine. So first of all, has anyone else been able to get into the cloud machine? You did. Anyone else?
Put the URL up again.
Sorry. Yes.
I've got the EarthData one done.
And let me make this bigger.
I'm in risk.open, so I've got
2i2c.cloud, yeah. And then once you've done that, they'll be spinning up a server and you'll be put into this repo with all of this stuff here. Quick show of hands, who's actually managed to get a hold of the repo or get into the machine or do anything? The rest of you are
still working.
Still working. All right, I'll give it a minute while you're trying that, and let me try and explain. There's a lot of material there. I'll provide the GitHub repo so you can clone the material. There's an environment.yaml file so you can actually create your own if you're familiar with using Conda. And I'll try and I'll sort of outline what I'd like to do today in about a minute or two. Let me just take a quick snoop around and see. Am I allowed to do this? Yeah, I think I can. Good. You're having trouble? Okay, yeah. I'm blind. That is frustrating. All right, I will, I'm gonna kind of see what I can do to sort of demo some things while I have you here. I was really hoping this would be more hands-on. Hopefully we can at least get you to the point where you started there. So there's far too much material here, which is okay, because what I really want to do is give you an overview of some things that you can do to get started. So I might kind of start at the end, actually. So we've got, I've laid this out. I did this in collaboration with some colleagues at 2i2c the International Consortium for Interactive Computing, and Métodos Ancia, which is an educational non-profit organization based out of Latin America. And we've got some support from NASA to actually develop these materials to encourage people to use EarthData Cloud. And I'll explain more about what that is. So some of the things we put together are providing a little bit of geospatial background for people that need it. How many people here actually have some familiar with geospatial computing and so, okay, that's what I would have expected. So I won't go through those notebooks, but those are there. I will refer back to them just briefly, just where we need it. Then there is some notebooks on. So what I'll do is I'll probably start on section 2 on software tools and talk about a little bit about some of the PyData stack, since this is a PyData conference. The PyData tools that we use for this kind of analysis, and just giving a brief overview of enough, sort of raster IO, X-array, HVplot, certain GeoViews, enough of these tools so that when we start using those in the examples, it'll be clear what is going on. You having any luck there?
I'm using my website.
Okay. But you managed to get it, okay.
Yeah.
Wonderful.
I'm just looking.
Great.
By the way, I was able to get it using VPN. So
A
if you-
VPN.
Yeah, if you have a VPN stuff.
Right.
That's interesting. Corporate VPN.
Okay. So I'll start in software tools section 2. And there's a whole bunch of notebooks. We'll come back to the test notebook. We could do a bunch of these notebooks without. Oh no, that's been converted to Markdown. That's why that was being funny. Okay. Sorry, let me go back to section 2. Okay, so I'll just talk briefly about the tools that we'll use for data manipulation, which is primarily X-array. How many people have used X-array before? Okay. So not everybody, a few of you, but so really there's other tutorials, so there's lots of tutorial material out there where someone can learn these things. I just wanted to show you enough so that when I'm using these tools later on in some of the case studies, that it's actually clear what is going on. So to start, of course, we've got a bunch of imports of all the relevant packages that we'll be using. And I'll start off talking about a particular one called Rio X-array, which is basically an interface for raster IO. So raster data is pixelated data, right? Just like you would have in an image file. So Rio X-array is basically a way of importing raster data stored in GeoTIFF files directly into X-array data array structures. So the other thing it also does is it extends the namespace of X-array's data array by an accessor called Rio. And that allows you to store additional information for what we call CRS, Coordinate Reference Systems. So part of the reason that working with geospatial data is a little bit tricky, if you just think about taking a raw pixelated image and plotting it with Matplotlib or whatever your favorite tools are. What you have is you just have a grid with a bunch of numbers in it that you can make an image out of and do a color map or p-color mesh or something of that nature. With geospatial data, you also often have coordinate systems embedded with this as well. So you have different projections, you have various kinds of mappings that are associated with coordinate systems. And so you kind of want to have a wrapper that keeps that tracked with your raster data. And that's sort of what this tool enables. So when you use Rio Xarray, you can, oh, is this going to work? Yeah, so I've got a file that is basically local on my disk that I'm running that takes 34 milliseconds to load. Right, and I just do use rio.openraster.io using that local path, and I load that into a data array that I'm assigning to the object DA. And I've got a remote file as well that takes about a second and a half to run. I mean, that's going to depend on what your network bandwidth is, where you are, and things of that nature. But you usually expect that, right? Like things that are going to be done locally are going to happen faster. And what you can do is you can actually just check. Here what I'm doing is I'm just verifying the X-array data array has a rich interface when you look at it in Jupyter notebooks. So you can examine all of the attributes of it and things of that nature. When I compared them element-wise, the .all method is just like the all function in Python. If you have a container of Boolean values, if they're all true, then they collapse to a single value true. If any of them are false, then that means it just does a logical AND of all of that entire collection.
Okay, I have an issue. I don't see the 0-1 data manipulation tool.
Which folder are you in? When you start up, you'll be in the folder 00 introduction.
Yeah.
So it's in 02 software tools.
It ain't there.
It ain't there. Oh my goodness. Can you try a pull from the Git repository? Why did that happen?
Was there for me?
Was
there for me? Was there for me on 2I2C?
Can you do a git pull origin main and see if that refreshes it? I'll take a look in a minute. Okay, so Xarray is a package. I won't go through all of this in. Hold on a minute. Let me hide this doc because it's getting on my nerves. Automatically hide and show the doc. Okay, so this will. There we go. That's what I'm going to do. I'm going to get more screen real estate here. So it's a way of basically just wrapping a NumPy array with some metadata, right? So just in the same way that a pandas series is a one-dimensional array that has an index and some other rich information embedded, so you can do certain manipulations a little bit easier in pandas. Xarray does that for multi-dimensional arrays rather than just single-dimensional arrays. And so you can take a look at sort of the rich wrapper for that and examine. It has coordinate attributes. It has indexes for coordinate systems. So when I loaded this data set from a file, associated with it is some X and Y coordinates associated with the pixels. This is a two-dimensional array, or a three-dimensional array, I guess, in this case. It has a single band. and you can see the coordinates associated with it. Right, so there's a pandas index for the x coordinate, which is increasing, which these correspond to geospatial, I guess, easting coordinates. The y here would actually be sort of the northing. And notice the y coordinates are decreasing as you go along. It starts at 4 million. Yeah, 4,725,000, then decreasing by 15. I guess it's measured in meters. That's not, million is still too large though. That's strange to me. So you can examine these things programmatically as well as through the through that rich array, and that is actually, this is being done in some of the examples we'll look at later on as well. So we can examine the dimensions of it, right, which have some labels associated with it, and just as we have in pandas, you can use the values attribute to extract the NumPy array associated with your underlying pandas data frame or series. You can use the .values attribute in Xarray to extract out information. And then you also have metadata associated with it, stored in the ATTR's dictionary. And remember, we loaded this using Rio Xarray, so all of this was sort of unpacked for us automatically. Yes, please.
What data set is this?
Sorry?
What data set is this?
I will just get to that.
Okay.
I'm just doing I'm doing the nuts and bolts first, just showing you how to do this, but I will explain the data set in a minute, in a few minutes. This is going to be, I think this is probably, here it is. It tells us maximum vegetation loss anomaly. So this is an example of the dist alert data, the disturbance data that corresponds to vegetation loss. But thank you for asking. I will get to that. The other thing I just want to mention, when we use Rio Xarray, it gives us some other information. So there's some other attributes associated in the RIO namespace. The main one that we'd want to use actually would be this CRS, this coordinate reference system, because that will be used when we, often when we load data up from a file, we'll want to plot the raster data into, using some of our tools, hvplot or matplotlib or whatever graphics library that we have. And we'll often want to underlay tiles underneath. And so when we're combining the tiling and the actual raster data, you need to make sure that the coordinate systems are lined up. And that's where this attribute is actually bundled into the data set. And we don't have to, and then we can keep track of it using the Xarray data structure as well. And we can set this and do other things of that nature. So the main thing that we use in some of the examples we have later on here is this CRS here, this coordinate reference system. And this is a code, this 5-digit code, EPSG. I don't know, I'm not an earth scientist. Can someone tell me what that means again? I know someone here will know better than I do. Basically, there are different, as I understand it from my earth science colleagues, there are standard sort of representations and encodings of coordinate reference systems that are given these identifiers that are stored in these kind of atlases or reference books, if you like, that are available online. And you can find these things out. And if you, I think if you just Google.
You wrote it right below.
Oh, I did. I wrote it right there. There we are, of course. EPSG. Yes, I did. This is the EPSG geodetic parameter data set. Right, so, and there we go. I even put a link to the Wikipedia. Okay, so the data array, like in pandas, there's a lot of sort of standard things you can do. You can rename, right? I can rename the x and y coordinates associated with this. So it has, instead of having X and Y, now that I've changed it, the da.coords has easting and northing, which are, I guess, the conventional labels for when you use universal transverse Mercator or one of these other kinds of coordinate systems. You can slice them using either integer slicing, using the iCell, right? So if you take a slice here in the easting coordinate from 0 to 2, that's non-inclusive of 2, so it only just extracts 0 and 1. So if I look at the easting, there's 2 values there, and the northing still has whatever it has, 3,660. Right? And so I've gotten a subarray, just like typical NumPy slicing or Pandas slicing. And then you can do, you can also slice by coordinates using the .cell method. And if you take this band 0, this 3-dimensional array that we've got actually, which only really has one array, there's a .plot API associated with the data array class, which mimics the .plot API in Pandas. And so we can get an automatic plot here, and if we look at this maximum vegetation loss anomaly, the values are ranging between 0 and 255. I guess that means it's probably 8-bit integers. Most of them are 0, which is why this plot looks pretty dark. There's better ways to do this. We'll look at this again in the next notebook. And there are some values that are higher here, and this would correspond to where, I guess, vegetation loss anomaly, I guess this would probably correspond to somewhere where the satellite has passed over and been tracking changes in the vegetation cover through measurements of surface reflectance, and there are periodic measurements being made. So I will talk more about this in a few minutes. Finally, you can take all of these things, you can get out, again, you can extract these things to NumPy and arrays directly. And you can also do things like if you take the NumPy array that you get from a data array, and you flatten it, and you put it in a Pandas series and use the value counts method. We'll use this. I like to use this one a lot. We get a kind of a histogram of what the pixel values are in our image. So we can see that most of them are zeros, and there's a bunch of values between 10 and 255, which sort of outlines the dynamic range. I think this is probably telling, and it says int64, I guess is the way it's represented when it's been imported, but probably the data file that it actually came from was stored with lower resolution. And the values are mostly between 0 and 100. Yes, that's right. And they're with the exception of 255. So what that probably means when we look later at the specification for this file, this is probably talking about percentage loss vegetation, and the 255 just probably means missing data. Finally, and I won't go into raster IO. I showed you how to load things with load files using RIOX array. Raster IO is a lower level way of doing things, right? It's more like the standard way of opening files in Python using a with block, right? Using a context manager. So, is there any reason why? Can someone tell me why I might want to do that while I'm as opposed to using RIOX array? Sorry? Yes, exactly. So streaming. So the reason that when I used RIOX array, it downloaded it found the data wherever it was located. You could give it a local file, you could give it a URL or a URI. And then once I did that, it immediately took that data and downloaded it to the local machine, this is my local machine, or a cloud machine, from wherever that source was. So sometimes you might want to query the data first. There might be metadata associated with it, like cloud cover, right? The percentage cloud cover. If it's like 90% cloud cover, you're not going to be able to see much in the raster data. So in that case, you might not want to bother downloading it. And you might be able to query the file by opening it using raster IO, and you only get 1 or 2, bytes of data being sent down the wire instead of the whole 3,000, million pixels or values all getting sent down the wire, right? So, and if you're being charged for it, then that would be annoying. So there's some tools for doing this, and there's some functions that we write later on in the notebooks in some of the examples that show this. Yeah, please.
Question. Does the format tend to be, you have multiple kind of binary files where you would be able to access the metadata, or you just have this kind of large file?
No, that's a good question. So the question is do you typically have multiple files or one or single files? So typically with cloud optimized geotiffs, what is typically done is rather than having, so many of the data products that are generated have, like 10 bands. But rather than having 10 two-dimensional arrays stacked on top of each other in a single file, part of the idea with cloud optimized geotiffs is to separate those into different files so that you can get one of the bands without having to get all the others. Right, so the answer is typically they're broken up into smaller chunks to make it easier for you to get the ones that you want. Make sense?
Yeah.
And I will actually look at that in a moment. I'm not going to go into the raster IO bit because I think that that's a little too much into the weeds. Let me leap to the end, actually, and show you where we're going to get to. So I'm in software tools. There's another file here, data visualization. I will do that one quickly, just to show you HVplot and some of the tools that we'll use for that. The next folder on using the EarthData, there's about 3 different notebooks. I'll go through all of those carefully, and those will describe the data products that we'll be working with. And then finally, I have some case studies. And the one I really want to show you is there's one here that is a template. And this is kind of what, this is sort of my take-home message for today. Because I've kind of laid out an outline of how we actually lay out an analysis in one of these notebooks. I've tried to put in a couple of utility functions in there in the template notebook, so that you can actually set up and do your own analysis and try and figure out how to find things that are interesting to you. But this is sort of where we're going to get, where I want us to get to before the end of today. Quick show of hands, who's actually been able to actually get a hold of this stuff and actually do some stuff? All right, so that's okay, thank you. This is the frustrating thing about being first thing on day one, is you don't get to debug these things beforehand. I only just got in last night. Okay. Yeah, mumbo, make excuses. Let's go back to software tools. I'll quickly take you through this thing on data visualization. Right, so I mean, one of the tricky things in Python is the Python visualization. There's a whole ton of different visualization libraries, right? There's Plotly, there's Altair, there's Matplotlib, there's Bokeh, there's there's holoviz and holoviews, and there's a sort of a family of libraries around that. And full disclosure, I used to work for Anaconda. I know Jim Bednar and Philip.
Rudiger.
Thank you. Philip Rudiger and Jean-Luc Stevens quite well. They're wonderful guys. And they developed the holoviz family of libraries. And there's a logic underlying them that is very appealing to me. And so I've focused largely on those. There is a little bit of matplotlib in here in one of the examples. And I want to be very careful how I state this because I don't want to be, especially since it's on video, there are many different tools, and use the ones that are most useful to you that you actually know how to use. But I think that one of the things that I tried to do, is the Opera repository contains a lot of examples of using this NASA EarthData Cloud stuff as well. And if you try and download those notebooks and try and work through them, you'll find a lot of them break initially. Yeah, it takes a lot of iteration to get it to work. And they also use every one of the libraries that you can think of. So it's very difficult to kind of read. So I tried to minimize these when we were making this up. So GeoViews is one of the holoviews family of Python visualization libraries that is specifically tailored for working with images in a geospatial context. So they have sort of built-in data structures for working with images, but they also have the coordinate reference system wrapped inside as well, so that you can actually make images that you can overlay on tiles and things like that easily. Right, so there's a couple of things. So one of the things I'll do first is I'll show, we can make a base map, right? And this is, by default, I'm using a sort of an interactive bokeh style of plot that's generated, which means I can zoom in, I can reset it to the original, I can use a mouse to zoom in different regions, and then I can pan, right, using these buttons on the side. That's a typical web way of doing things with web visualization. So, so what I want to do is I can do something, I can plot the coordinates of Tokyo. I do that by making geoviews.points. I make a list of all the points I want to plot. I can specify options using the options data structure associated with the GeoViews class, GeoViews module. And I've assigned bound those things to objects. And when I put these things all together, the asterisk, when I take two objects of type holoviews elements and I combine them with an asterisk, that's basically doing an overlay. So that's the same, and I'm specifying the options to apply to that. It doesn't look like much at the moment because I'm too far zoomed in. When I zoom out a little bit, I can see, oh, this is actually in Tokyo. And the base map is actually giving me, I guess, street names in Japanese. We could also start out with the global extent equals true, oops, and then zoom in if I really want to. I could also specify a rectangle by a bounding box. So if I have a rectangle that has left edge with xmin, right edge with xmax, the bottom edge with ymin, and the top edge with ymax, I could write the corners out as ordered pairs with xmin and ymin and xmax and ymax in different permutations. Or I could just write 4 numbers down, the bottom left corner and the top right corner. That's a standard way in graphics of representing a bounding box. So I'll just write a little, you can do that if I start with a point and I say I want to make a point with a rectangle with center at point and width dx and width dy, I can do that with a simple comprehension in Python, and you could do it in one line, but I'm just putting it in a function so that I remember that, because we'll use this to specify an area of interest when we're actually sort of setting up queries with EarthData Cloud. Right, so, and we'll also use this so here I'm taking, say, the coordinates of Marrakesh, which I think is in Morocco. Is that right? Yeah.
Yep.
And I'm saying, so I've got the longitude, latitude coordinates. I've got the, I'm saying I want one that's 0.5 and 0.25, width in longitude and height in latitude, I guess. And so there's a utility in GViews called rectangles, where I can take that bounding box, I put it in a list, so I can make a whole bunch of rectangles like that. I can specify the options for it in the data structure. And I can also make a point for the center, and I can put those together into a single plot. And there I have a plot of that bounding box with Marrakesh at the center of it. Right, so we'll use this to when we're actually setting up queries for the EarthData Cloud to set up what we call an area of interest, which is just a bounding box, so that we can make queries using the PyStack API. And I'll explain more what that is in a few minutes. Finally, one thing I just want to also point out is hvplot is another utility that, and that's built to extend the pandas.plot API. So there's a whole bunch of libraries that actually use, I think actually Plotly also does this, and a few others. And the idea is that if you have a common API for these with different data structures, so you can attach a .plot namespace to a pandas data frame, to an X-array data array, to a DAS data frame, and various other kinds of objects. And you can use that to produce graphical output. It means there's fewer things that you have to learn, and it makes it easier to use. Right, so just as a quick example, right, here's a pandas data frame that, I guess when I made this up, I was talking at SciPy in Tacoma, and so I chose cities on the West Coast, and I live in Vancouver as well. So, although it's fun being here in New York, I haven't been here since before the pandemic. All right, so these are, what are these doing? These are just daily recordings of temperature, I guess, I guess that's in degrees Kelvin, because those are very large. Those definitely aren't Fahrenheit. And they're not Celsius either. So let's just take a smaller subset of those. We'll just take the West Coast cities here. And if I do westcoast.plot.line, that makes a very messy picture, because of course it's all, I guess, this is sampled over a long period, over several years, and you can see seasonality in it. So that's using the standard, this is a matplotlib plot. So that's a static PNG that has been rendered in my Jupyter notebook. With hvplot, you can choose different backends, but it's basically just mimicking that. So instead of doing plot.line, I do hvplot.line. But I've chosen, the backend is bokeh, so it's interactive, which means I have the ability to zoom in and do various other things like that. And this is a nice thing to do when we're playing around with our EarthData imagery, because we'll want to be able to explore this thing easily, right? So here I'll make some options. So I put in a grid, I've specified the height and width. But I can also do things like I can, because it's a pandas data frame with time on the index, I can do something like resample it by every 2 days. So I take all the measurements, I average those. So that will have the effect of smoothing this out. So I've got a smoothed data frame that I generate from that. And then I get something that I can actually resolve a little bit more clearly. Right? And we'll use tricks like this again in some of our case studies as well later on. Finally, that plot API, as I mentioned, it's also extended into Xarray. So if we import hvplot.xarray after importing Xarray, we can load a local geotiff file. Right, so again, this is probably that same one I looked at before. Oops, what did I do wrong there? Oh, I forgot to do that myself first. There we go. So I've imported it. I do a little bit of reformatting to my data array, right? I relabel the coordinates. I squeeze out that extra dimension so that it becomes a two-dimensional array. And then I can plot it. This is, again, doing a matplotlite plot by default. And I guess it uses p-color mesh. And this produces that plot that we saw before in the previous notebook. But I can use the image plot by default in hvplot. Oops, there it is. That doesn't look great. But we can actually improve this incrementally. Right, so I've labeled it easting and northing. The aspect ratio is all messed up, and the color map is not very good. So let's try and speed this up. So what we can do is we can speed up the rendering by using the options rasterize and dynamic equals true. And what I'm doing is I'm putting these options in an image into a dictionary. The reason I'm doing this, what I'm doing here is I'm going to slowly build this up to show you how I built up a plot. Later on, I'm going to show you plots where there's a whole bunch of options that are thrown in. And but typically, when you're doing these interactively, what you'll do is you'll build it up slowly. Right. So I've made that dictionary. Now what I'll do is I'll call data.hvplot. I'll specify the arguments of the coordinates on the horizontal and vertical axes. And then the extra optional arguments are coming in by dictionary unpacking. I'm getting some warning there. Okay, so that was a little faster. Now let's fix the aspect ratio. So since I started with a dictionary called ImageOts, remember when the update method for a dictionary, I can add new things to it. Right, so when this basically just creates three new, this adds these three key value pairs to my dictionary. And then when I make the same plotting call, now this new dictionary is being put in there. So I'm just slowly building up the options. So now it is, let me make this a little bit smaller, just so I can see that. There we go. Okay, so now it's at least square because my image is 3660 by 3660. I'll add a color map. I'll use color map hot. I'll also clip it. Remember when I was plotting before, the image had values between 0 and 100 and then 255. So I will set the limits being from 0 to 100. And I'll also set a transparency value, alpha is 0.8. Right, so again, I'm just slowly building up this dictionary, and now I have something that's a little bit clearer to see. I'll put in the coordinate system because what's going to happen next is I'm going to put a base map underneath it. And if I want this raster data to line up correctly with the base map are usually, I think they're provided, the tilings are often in Web Mercator or some other kind of coordinate projection. And so whatever the coordinate system is used to save this data that was stored in the data file, I want to make sure I'm restoring that. So, I've just added that. I've pulled that in from my X-array. I'll add it to my options, my image options, and then that doesn't produce any difference at the moment. So I'm going to make a separate options dictionary for label lots, where I'm putting things like the title and the labels for the axes. Full disclosure, there's a little bit of black magic in this, and I was asking Jim Bednar about this, one of the developers of HoloViews and HVPlot and GeoViews and and all of this. The options system for HoloViz, it isn't always obvious where you're supposed to put them when you're modifying things. You try it until it works, and that's more or less, there's a logic underlying it, but that requires that you really understand a lot about the rendering engine and bokeh, a lot of the details underneath. I guess I'm passing this, don't shoot the messenger. If it seems like black magic, it's kind of because it is. So now I've got a title, I've got the axes are labeled now with latitude and longitude, which is what I want them to be. And now let's put on the base tiles. The base map, and when I put on the base map, of course, I can see, wait a minute, there's actually a lot of white pixels that correspond to 0. So I can filter those out using a where clause like you have in NumPy arrays, right? So I'll filter out all the ones that are strictly positive. I've clipped out the ones that are 255, which are missing data anyway. And then now I get a slightly more usable plot. And this is showing percentage vegetation loss. Actually, I don't know, we'll take a look at that in the next notebook. But this is actually a much nicer picture, sort of now that we've kind of got there, right? But you can learn all of this stuff about the HoloView. You can use other visualization tools. This is just one I'm using. But I wanted to give you an idea. This is kind of how, when you look at some of the examples, when you look at the Opera examples, there's a lot of, it seems like they're really convoluted like that. Okay. Let me move on to using the Opera data. And let me tell you exactly what all of this means. So if I go to folder number 3 using, okay, so the Opera project stands for Observational Products for End Users from Remote Sensing Analysis. So this is something that NASA has done, providing all of these data sets, and in practice what they are is they're pre-processed data sets. They're things like surface displacement, surface disturbance, surface water extent, vertical land motion. We're going to be looking at these two, surface water extent and surface disturbance. Disturbance you can think of as, so there are a bunch of satellite missions, the Landsat satellite and the Sentinel A and B satellites. And those are orbiting the Earth taking measurements of every tile on the Earth measured in the military grid reference system every 12 days or so. So the harmonized Landsat Sentinel data basically takes the combination of the inputs from all of these to make these data products. So surface disturbance, that's basically looking at reflectance, looking at vegetation. So if you think about the satellite passing over a jungle, and then the next time a satellite passes over a jungle, it notices, wait a minute, there's less light coming off of there. What happened? Maybe. And so this is often used for forest fires. The surface water extent is often used for quantifying floods and droughts. Right, so it's about moisture content on the surface, bodies of, so water that is on the surface of the Earth, of the land masses, and not in the middle of the ocean. So there's do I have a link to the repo here? I don't. There are, but I think that's probably in the abstract for this. So they take basically this raw data and they make these data products basically that summarizes, that is done by some algorithmic pre-processing. So you're not actually looking at the raw data. You're looking, these data products constitute some pre-processed work. So these are, I'll start off talking about the land surface disturbance product, which again is measuring vegetation disturbance. So we actually just looked at one of those files. So let's just take a look. Again, I've got these stored locally first, but in one of the next notebooks, we'll finally start playing around with the stack catalogs to actually download these things remotely. So when you get these files, you download them, or when you find them using the stack catalog, they will have a name like this. And that name encodes metadata about the, right? So we can actually split that up. File name.split on the underscore character. So opera is just the name of the project. L3 refers to the level of some version number associated with the project. The kind of product, which is a dist alert HLS. There's also HLS stands for Harmonized Landsat Sentinel. So that means it's coming from both the Landsat and the Sentinel missions. Alert, there's another one called dist-an, which is basically an annual summary of the disturbance product. The alert is taken at every 12 days or so, or whatever frequency you get. This T10TEM is an identifier in the military grid reference system. So that tells us, I think I've got a link up here. Right, so basically the military grid reference system, you have these universal transverse locator has these vertical bands, which are identified by numbers from 1 to 60. I guess because they're broken up into every 6 degrees. And then these vertical lines are about every 8 degrees of latitude. I always mix up longitude and latitude. And then each one of these is subdivided into squares that are about 100 kilometers by 100 kilometers. And then and those images, then when they're done at 3660 by 3660, that works out to about 30-meter resolution per pixel. So, the numbers from 01 to 60 refer to one of these big squares. The letters from C going up to X, leaving out I and O so that they don't get, so that they're non-ambiguous, so they don't get confused with a 1 or a 0. So there's 20 big squares, and then There's another 2 letters that refer to when you refine these things to 100 kilometer by 100 kilometer boxes inside. So that is a tile ID. There's a timestamp. There's 2 timestamps. One corresponds to the acquisition time. The other corresponds to the when the data product was produced. So I guess this was acquired on the 15th of August 2022, and the data product was produced on the 17th of August 2022. There's a timestamp associated with that.
I have a question.
Yeah, please.
So if the timestamps are 2 days apart, but the data is only taken every 12 days by the satellite, would there be much difference? Like if you had it set to all of the 12 days?
So I think each the Landsat and the Sentinel each cover every tile every 12 days. So in fact, there'll be the frequency. So this is one of the things that's a little bit difficult. If you take a given tile and you want to try and do an analysis of that, you're not necessarily going to get measurements every day or at regular intervals. You're going to get 2 that are together that maybe over 2 or 3 days. Then the next one is 5 days later. So it's at least. So each one is due once every 12 days, and generally you'll get.
All the tiles?
Yeah, all of the tiles will be sampled by one of the satellites every 12 days, and you will have generally within 12 days you'll get at least 2, possibly 3, I think. Yeah.
I want to know, like, how real time is the information process? What's the most recent data that we could get from this specific?
So when I show you the stat catalog, I'll get to that question for you. Where am I at here? Okay, I'm going to hurry through this. Right, so this is some more of the same data. Let's plot this up again. So this is band 1, the maximum anomaly, and as I said, it's a percentage here, with 255 being missing pixels. So we filtered out the 0 pixels, which is no disturbance, and 255, which is missing data. So this is basically the same picture we had before in that last notebook. But we can do this for other layers, other bands. And coming to the question over there, oh wait a minute, there's I don't know how many bands there are in the disturbance, but I think there's about 10. Right, so here this is the date of initial vegetation disturbance. And I think this is represented as an integer, right? So this is a bit of a confusing thing now. Okay, let me see. So if I take a look at this product, I have dates between 247 and 592. And if I look at the specification, here we go. That's taking a while to load. You can read in the spec all of the there's tables that summarize all of these items in here, all of the bands. There's the military grid reference system, and that's the dist-and product. We got dist alert. There's all of this metadata that comes with it. Anyway, I think, okay, what is this? The Sentinel, so -1 is, so this is stored as integer data. -1 is a Sentinel value for missing data, Any positive value is the number of days since December 31st, 2020, in which the first disturbance is measured in that pixel. And I think it's also within the last year. No disturbance in the last year. So I think this measurement was taken on the 22nd of, August 15th, 2022. So within the last, so 1 year before that is probably day 247 since December 31st, 2020. And 1 year after that is probably 592. So that's where this range of integers comes from. So you have to read the spec to actually figure some of these things out sometimes. It's a little bit tricky. I'm not going to go through all of these bands because I think that there are more interesting things to do, but you can sort of see, again, you can generate these plots, and by going through and reading the spec, I set the limits on my color bar here to sensible limits so that I would, because of those are determined by this particular data set. Okay. What else have I got in here? Yeah, there's more in here. There's another the vegetative status, but I won't go through that. I will actually, maybe I'll do it just quickly because this one only has, this is a categorical data set. So basically there are provisional first detection, a confirmed disturbance, provisional with change bigger than 50%, confirmed with change bigger than 50%, and so forth. So there's another band. So this and the rest. So this will be stored, I think, using 8-bit unsigned integers. And so. And again, we can. This is again a continuous color map. What we can do is we can actually write up, set it as a finite number of values, which I'll do quickly with the next. You know what? I'm not going to do that because I've only got 15 minutes left, and I want to make sure that we do at least one example. There's a similar product. There's a similar description of the. No, that's not the one I wanted. Oops. Going up to folder 3 again. There's the DSWX, the surface water extent, which is a which basically shows you sort of the groundwater. And I guess there's some examples in here of actually, again, this has only a finite number of different values in the pixels. So again, it's stored as integers, so you can actually create a color map that basically has a finite number of bands that corresponds to where you've got water here. I guess this is supposed to be the Suez Canal. There's cloud cover, which is what this gray is, which is why we're not actually seeing a lot of exposed water that you can see when you look at the tile, the basement underneath. So there's 10 layers to the DSWX product as well. And again, that's used for tracking things like flooding and drought kind of conditions. Okay. So the PyStack API. So I've showed you now a whole bunch of tools in Python for actually playing around with these files, and all of the files we've looked at right now have been locally gained. So what the Stack API is, Stack is a spatial temporal asset catalog, and there is this sort of, you can look through NASA EarthData search to find examples of these files. And what you would do is you would do something like you type disturbance and maybe, yeah, actually maybe just do dist alert. And you can see, and what you get is this says there's, so coming to your question a few minutes ago, when can you get these, what is them? So for instance, this Opera Land Service Disturbance Alert for Harmonized Land Sentinel-2 product, there's 7.5 million granules that correspond to 2022-0101 ongoing. So you could do a search. If you did a search before that, I don't think you get anything from this particular catalog. And you can specify a rectangle, right? What's a little bit annoying, at least I find it annoying, is that this specifies the rectangle in latitude, longitude instead of longitude, latitude. So when I try and cut and paste these from my notebook, I have to reverse the order of these manually, which is a bit annoying. But you can do that. Okay, so this is where I kind of really wanted to make sure we get. The generic pattern that we'll do in these kinds of analyses is to specify an area of interest and a time window. We have to specify an endpoint provider and a catalog identifier. And those are, I mean, I'm going to have to admit, I find it tricky to figure these things out. I've tried asking my Earth Science colleagues specifically how to do that. I tried doing a search on search.earthdata.gov and play around with it. So let's just do an example here, right? So here we'll look at floods in Texas from last year. Right, so we'll just import a bunch of libraries we've been playing around with already. To use the PyStack API, we have to do, this is a little bit weird to look at, and if you don't do this, it will screw up. This is basically configuring the environment so that it knows, and it will also take a look at your EarthData Cloud credentials stored in your netrc file. So here I'm going to just define Livingston, Texas. I'll make a little bounding box. I'll plot. So just as a check, I can sort of draw a picture and see, yeah, that's where my area of interest is. I can specify my time window, usually as a string, and I'll put these into a dictionary with my bounding box and my date time. In order to do this search, I need to know an endpoint, a provider, and the name of the collections. And these things occasionally change, which is a little bit frustrating because I had to hunt a little bit to find these to make sure this works. So sometimes that takes a little bit of tweaking. And you can ask about that. There are some issues on the NASA CMR Stack GitHub issues where you can get those. Oops, I forgot to do this. Right, so now I've got a whole bunch of search results. Those search results are each what you call a granule. So a granule you can think of as a single observation by a satellite. So while the satellite is over a tile, it takes a whole bunch of pictures with instruments, it stamps a timestamp on them, and then those get bundled into the different layers of our dist or our DSWX data product. So if I look at the output from this, I can see it's got a rich interface here. So there's things like the date time, which is when the data was acquired. There's some geometry as well. There's another one here that's called assets, and these are the different layers of my dist data product, right? The that you can read about in that in the spec. So what you can do, you can take a look at what all those things are. The important thing is the assets have they have names, but they also have an href attribute, which contains the URL where you can find one of those files. So then what we can do is we can split that, we can extract that, and we can get things like what the tile ID is and various things from that. So we can put that into a function that basically makes a data frame out of it that we can use to process our results. And we can clean up the data frame by getting rid of some extraneous columns. Oops. I hit that twice. We can clean up the schema. So I basically got a data frame that summarizes all of this. But this allows me to do things like, you can see that the cloud cover is missing some elements sometimes. So we can refine those and do other kind of computations with them. Right, so I can filter out wherever the cloud cover is less than 50%, right? And I can use sort of usual pandas operations in order to trim down the searches. And then once I've done that, I can retrieve that URL, which has all of the interesting stuff in it. So I can do things like I can filter out one particular band, right? So I can filter out the B01 water band. And also figure out which ones belong in a particular tile in the military grid reference system. And I can put those all together in one data array if I like. Right, so I've got a function here that takes that data frame and stacks it all up into, so right now it's actually downloading those from remotely and putting those into a stacked data array. That's going to take a minute. There's one last one I wanted to show you here. Let me try and do this quickly while that's going. Again, so my goal really was to show you this in I know I went through it very quickly, and we had 90 minutes instead of 4 hours, so it's a little bit tight. But the main thing is I want to show you this template so that you can actually go through these and actually work out how to do this. So this is a nice example here, using disturbance data, right? So again, so here I'm just putting together the utilities that I would ordinarily put those into a module if I was writing Python code. I'll just define the place near the Dhavide forest in Greece. I'll define the endpoint of the provider and the collections. I'm going to find dist data products for this. I'll do a search. And I'll bundle those all into a data frame, and I have a data frame with how many? I'll clean up those columns, turn the date. I'll drop the extraneous date columns. I'll turn the date column into date time and put it on the index. I'll take the cloud cover and make that into a floating point number. And I've got 828 granules associated with this already. So we can do a little bit of cleaning. We can see these all have the same tile. The assets are a little bit messy, but we can pull out the ones that are the veg disk status by getting a Boolean series. And that Boolean series then we can extract and refine into my data frame. So now I have a smaller list, I think of 36, and I can resample those. What I've done is I've resampled them by days, so I've got a list, however many, if there's 2 measurements on the same day, they're in a list in that column instead. So what this allows me to do, I can use a merge, and I can pick out all the places where I've got confirmed greater than 50% damage. And what that will do, this will take a bit, it's going through all 30 files. But what it's going to do is, and I'm doing a calculation basically counting all of the pixel values 6. And I'm going to color those red. And when I do this, I'll get an idea of, and add those up. Each one of those pixels is 30 by 30 meters. And so that tells me how much area has been damaged by wildfire. This is basically corresponding to a wildfire. And we can actually do a little visualization that shows the spread of the wildfire, which is actually kind of cool. Unfortunately, this is downloading all of this data and it's taking a little bit of time. I'm going to run out of time. I've only got a minute left, so let me execute the rest of this. But so thank you for your patience with the technical issues there with the firewalls. I hope that I'll make sure that you can get this repository at least. And then there's an environment.yaml file in there as well, so you should be able to reproduce the environment and run it on your own machine if you like. I had also a form to send around. I don't know how to get that link to you. I will share that with you promptly. But I hope that you've got a sense, though, of what these data products are. You've got a sense of how you can actually use those, how you can, once you've set up your EarthData Cloud account, and how you can actually sort of set up your own prototype analysis based on the template that I showed. So again, thank you for your patience with the technical issues, and I'm happy to take questions. You can see me around at coffee, and let me know if there's anything else that you want help with. So thank you very much for your time.